Hi everyone. So this is the last lesson for today, lesson 2b, which is going to be about curved mirrors. So this is going to be similar to the last lesson in that you are looking at ray diagrams and mirrors and trying to figure out what images look like. But this time we'll be applying these principles to curved mirrors rather than flat plane mirrors. Okay, so learning goals for today. We're going to draw ray diagrams for curved mirrors, as we just said. We're going to analyze these analyze images in curved mirrors using SALT. So this is going to help us analyze images, and also if we understand SALT, we can think about what type of image we are supposed to get, but you're also going to need to have some new vocabulary to understand how all this works. Okay, so curved mirrors. There's going to be two types of curved mirrors that we're going to be considering, concave mirrors and convex mirrors. So concave mirrors look like this. It can be confusing because convex mirrors kind of have the same shape. So what's important to know here? Well, what's important to know here is that for a concave mirror, it's shaped like a C, but the ends of the C bend towards that person. So it's almost like a little cave that you can walk into if you like, concave. So you know that because the lines are on the outside. When you see these drawings of a mirror, the lines that kind of stick out like this are on the side of the mirror that does not have the reflective surface. So the reflective surface is here. SpongeBob can look at himself through the concave mirror. A convex mirror is bent the other way, so the C bends away from the person, and the reflected surface is in this region here. So here we have SpongeBob looking into a convex mirror. Okay, so these have many applications. There are many reasons why you might want to have a curved mirror, and you'll be able to see why based on the characteristics of the images they produce, based on the SALT. Because sometimes you don't want to have just a life-size, real-looking image of something. There are reasons why you might want to have other images. So, for example, I kind of alluded to this before. If you have a makeup case, you want to look at your face, or if you have a hand mirror, it might help to have something that makes your face look bigger, so that you can notice small things if you're applying makeup. Or if you have a hand mirror, if you're examining your face, if there's something that you're looking for, then that might be useful. On the other hand, if you have a store and you're worried about maybe some of your things being stolen, you might want a mirror that makes everything look smaller. That way you have a larger field of view, meaning you can see more of the store just by looking at this mirror, so you can kind of keep an eye on more parts of it. And we have a similar principle with car mirrors, where they make things look smaller a little bit so that you can see more of what's going on behind you. You might want mirrors that bend light in a way that's not straight. So, for example, this telescope here is a reflecting telescope. This is actually the same model that I have at my home. And it basically, you want it to collect as much light as possible. The slang for these in the astronomy community, they sometimes call these light buckets. So you want them to collect as much light as possible so you can see things that are far away, but you need that light to get bent so that it will reflect through the eyepiece and you can see all of that light. So you might want a mirror that bends the light inwards. You might want a concave mirror here. Okay, so let's look at some ray diagrams so we can get an understanding of what the images produced by these mirrors look like. We're going to need, as we said, a little bit more terminology beyond just concave and convex. We're going to need to know about center of curvature, focus, and vertex. So imagine this is a mirror. So in this case, you'd have an object somewhere on this side. So what kind of mirror would this be if the object's on this side? Hopefully you know this is a concave mirror. It bends towards the object. And so we would call this black line where the object could be placed that goes through the center of the mirror here. We would call this the principal axis of the mirror. And we have a C and F and a V. The V is the vertex where the principal axis intersects with the mirror. F is something called the focus, which is mathematically important, and it is going to be important for the way that rays kind of bend, as we'll see in a moment. The center of curvature is twice the distance from the vertex to the focus. So sometimes this is called 2F or it's called C. But if you imagine making this into a circle, the C would be the center of that circle, the center of the curve, if you like. So that's going to have a couple of important attributes associated with it as well. Okay, so as long as you know these four things, you should be fine. Okay, so let's start seeing what kind of images these mirrors produce. So to do that, we need, there's one more thing we need. We need two main principles. So the principles are that the incident rays parallel to the principal axis, so if you've got rays of light coming like that, straight, and they're parallel to the black line, when they strike the mirror, they will reflect through the focus. So the reflected rays will go through the focus. Incident rays that pass through the focus will reflect parallel to the principal axis. Okay, let's see what that means. I am actually going to be able to, I think, do an example in Paint for you because drawing these lines is a little simpler. So suppose I have an object here, and I want to see what kind of image this produces in the mirror. I'm going to keep those two principles in mind. So principle 1, a ray that is parallel to the, a ray that is parallel to the principal axis. So I want it to be straight, just like the principal axis before it hits the mirror. It's going to hit the mirror there. So a ray that does that is going to go through the focus. So it's going to go down there. Just going to extend this right there. So that's from the top of the object. I could do one from the bottom of the object. The bottom of the object, if it goes through the, if it's parallel to the principal axis, it's going to just go along the principal axis, going to strike the vertex. And if it's going to go back through the focus, it's just going to go back the way it came. So I'm not going to draw my second line for the bottom. That just is the principal axis. Okay, from the top again, a line that goes through the focus. This is principle number 2. So a line that goes through the focus and strikes the mirror is going to reflect back parallel to the principal axis. So there we go. Should be parallel again, should be straight. Look straight. Great. Okay, so I now have two lines from the top, so I can see that where those two lines intersect, that's where the top is going to appear. So the top is going to appear there. And if I'm looking at my second line on the principal axis, if it goes through the focus, it will hit the vertex and bounce back parallel to the principal axis. So again, from the bottom, I have the same line twice, and that line is just the principal axis. So the bottom of my arrow is going to be the principal axis, and the top of my arrow is going to be here, where those points intersect. So I'm actually going to get my arrow in here. Okay, that does not look like the arrow, so maybe this paint thing was less of a good idea than I thought, but hopefully this will give you the idea. Look a lot bigger. There we go. So that's going to be our arrow. So if we were going to assign salt attributes to this, how would we do that? So size. How does the size of this image compare to the original image? Well, it's smaller, right? So size is smaller. Attitude. Is it upright or is it inverted? Well, it's upside down, so it's inverted. Location. Where is it? So it's between C and F. And the type of image. Is this a real image or is it a virtual image? Do we actually have light rays intersecting, or do they intersect behind the mirror? So you can maybe, as you can see in this case, this really does stem from the real intersection between two light rays. The two reflected rays that we have both cross at this point. So this is a real image. Okay, so this image is in front of the mirror, and the image could be projected at this point. So you could actually see it here. But in any case, that's how you can use this sort of situation to create your image. And what this shows you is that if you have a concave mirror and the object is behind the center of curvature, this is what you're going to get out of that process. Okay, let's go back. So here, yes, okay. All right, so the first case for concave mirrors, we're going to break this into a few different cases. I think there are 5 cases, if I remember, for concave mirrors. If you don't know these cases, you can just figure them out. Like the first case here is what I just did. If you have an object that's behind the center of curvature, and you analyze it with one of these diagrams, so again, remember that the line from the top, if it's parallel to the principal axis, it will go through the focus. And if it goes through the focus, then it will come back parallel. And so you just get the point of intersection for the top. The bottom is just along the principal axis, and you draw your image. And so you'll notice for this picture, it's the same thing that we just did, right? The image is smaller, it's inverted, it's between C and F, and it's a real image. So whenever you have an object anywhere here beyond C, these are going to be its characteristics. But what if you took this object and moved it at C? Well, I could draw that and figure it out, but I'm not going to do that right now because that's going to take a little bit too much time. So I am just going to show you the answers. But please make sure that you can draw these. I am going to give you some practice questions in addition to your final assessment with this stuff on it. Sorry, when I say final assessment, I don't mean final exam right now. What I mean is the final assessment for Unit 2, for Lesson 2 for today. So what happens if we put this object here? Okay, well then you're going to get this case. Whoops. Case 3. I forgot case 2. Great. Okay, well, let's do case 2. We'll do it together. So I will do this one. Okay, so case 2 is what if you're at the center of curvature? Oops. Okay, so very quickly here, if we draw a line, let's make that middle an arrow. If we draw a line going along the principal axis, it's going to strike the mirror, and then we're going to come back through the focus. Similarly, if we draw a line through the focus, we're going to come back. Through there, and what you might notice is if you look at this now, well, what do you know? I did it right. I might not have done it exactly right, but you should hopefully get the idea. You get the same arrow, but upside down. Okay, so if we were going to use salt on this, we would say that the size is the same. The attitude is still inverted. The location is at the center of curvature, and the type is virtual. Okay, it might look a little bigger. I actually think it does actually look a little bigger than my top arrow. Part of the reason for that, though, I think is because you can see that my line here, this line doesn't go perfectly well through the focus. I was rushing a little bit. So this line should actually come higher up. You can see it doesn't go through the middle of the focus. My top line is okay, but this line should be further up. But in any case, hopefully you get the idea. Okay, so that will be added in once I upload the note online, but for now, that's case 2. This is case 2 at the center of curvature, produces an image at the center of curvature that's the same size but is inverted and is virtual. Sorry, this is not virtual. This is real. Oh God. This image is real. Okay. Back we go. Okay, case 3. What if the object is between C and F? Okay, well in this case, again, you just follow the exact same patterns, right? Line that goes and hits the concave mirror goes through the focus. Line that goes through the focus comes back parallel to the concave mirror, to the principal axis. And you end up producing an image over here. Again, that's where the crossing of the two lines happens. So you'll notice that this image is definitely now larger than the real object. It's still inverted. It's beyond C, so it's headed more to the left, and it is a real image again. The light rays actually do cross. Only a couple more cases. Case 4, what if your object is actually at the focus? So this one is weird. If you draw a line that hits the concave mirror, then it will go through the focus. You can't actually draw a line through the focus, really. Like, how would you do that? I guess you could, no, you can't really do it. So there's another principle that you can use here. I put this further down into the presentation, but I probably should have moved it up here, and I think I will later on. And that principle is if you don't have an easy time drawing a line through the focus, you can use your basic law of reflection, where the angle of incidence and the angle of reflection are equal. So that's true at the vertex here. So if you draw any arrow from the object to the vertex, it's going to behave like a plane mirror at this location. So the angle of incidence here and the angle of reflection will be equal. So if you draw that, what you'll notice is you get these two rays, and they're not they're parallel to each other. So there is no point where they're going to intersect over on this side. So there's not going to be any image produced here. Well, we know what can happen in that case if there's an observer looking at these two parallel rays. They can extend these parallel rays behind the mirror and maybe create a virtual image. But you might notice if they're parallel in front of the mirror and you extend them back, they're going to continue to be parallel behind the mirror. So there's no way these light rays will ever cross either in real life or virtually, which means you're not going to get an image. So if you have an object at the focus, you get no image of that object in the mirror. You can try this, by the way. There is, if you have a concave mirror, you can do this. If you have like even a metal spoon, if you orient it in the right way, you'll see upside down images of yourself. And if you move it so that you eventually end up at the focus, you'll see everything goes blurry, and then you don't get an image. What about if it's beyond the focus? We've been sort of starting out in front of the center of curvature, at the center of curvature, in between the center of curvature and the focus, at the focus. What happens if you put it in front of the focus? I mean, you get no image at the focus, so do you still have no image if you put it here? Again, if you have a spoon and you try this, you'll see the image flips around all of a sudden, because once you put something in front of the focus, then you can, well, there's a couple of ways you can do this. So you could do this with the usual sort of principle, so going from the top of the arrow and then parallel, hitting the mirror, and then going through the focus. You can use that vertex method that I just mentioned above, where angle of incidence equals angle of reflection. You could still actually use the focus method in this case, but what you can have happen is have a line going from the focus, touch the top of the object, hit the mirror, and then that will go parallel this way, and you can extend that behind the mirror to create the image. That might sound really confusing, but if you look at the video that I put at the end of this presentation, you can use that video and watch it. It's better explained there. So let me just actually explain it in the context of what's put here, because you have the option of doing this as well. Okay, so you can see these light rays when they're coming out this way in front of the mirror, they are diverging. They're not coming closer together, they're going further apart. So they're definitely not going to intersect here. They're just going to keep getting further and further apart. So there's no way you're going to get an image in this area. But the brain, as we know, with plane mirrors, can extend the lines backwards, the rays of light backwards behind the mirror. And it turns out if you do that, they actually will intersect behind the mirror. So what you're going to get is a virtual image, like you get with a plane mirror. So it's going to be upright, right? You're going to have to extend these lines backwards and then put the point of intersection there. That's where your image will be. So it'll be an upright image. It's definitely larger than the real object. It's behind the mirror. And it's a virtual image, right? The light rays don't really cross, but they end up back here. So you're magnifying things when you do this. So maybe that might give you some ideas on applications you can use if you're magnifying an image, making it look bigger in this particular case. All right, so that's it for concave mirrors. You've got those 5 cases, but what about convex mirrors? The nice thing about convex mirrors is you only have one case, and here it is. So this is where I put that extra principle. Apply the law of reflection at the vertex. So I should have put that above because you're using it for here and you're using it for here as well. But this is what I meant. So angle of incidence equals angle of reflection at the vertex. So if you have a convex mirror, that's pretty easy. You just draw a ray, hit the vertex, and it will go this way, and these two angles will be equal. Right? Your principal axis in this case is functioning as the normal. So your angle of incidence is there, and your angle of reflection is there. What about the other line, though? You'll notice the other line follows a principle, but it modifies it slightly. So if a line goes from the tip of the object and it's parallel to the principal axis and hits the mirror, when it strikes the mirror, it's supposed to go through the focus. But you can just kind of even, maybe with real life experience, think about this. If you ever threw like a tennis ball or some kind of ball at a wall, rubber ball, and you throw it at this kind of wall, it's not going to bounce down here. It's going to bounce this way, right? So how does that connect with the focus? Well, there's a focus behind the mirror, and that focus is the same distance from the vertex as this focus is. So you can think of this as another focus. So the light ray will bounce out this way, but if you extend it backwards, it will virtually go through this focus. So that's the key here. make sure you realize this light ray is going to go out like this, but if you project it backwards, it will go through the focus on the opposite side of the mirror. And now what you've got are two virtual rays that do intersect here. So your image is going to be behind the mirror, and it's going to be quite small. But it's going to be upright and it's going to be virtual. So you get a nice upright image, but it happens to be smaller. So remember we mentioned some of those cases with car mirrors and mirrors in a store. You can maybe see why this might be useful, right? You get a small image, so you get more of a field of view. You see more from the world around you, so you can see more of what's going on. Okay, so the image is smaller, it's upright, it's behind the mirror, and it's virtual. And that's everything I've got for this concept. Check out this YouTube video if you want to. They explain curved mirrors a little bit more. They're able to more effectively draw the diagrams than I was, so that might be useful to you. So make sure you practice this with a few examples, and then you can complete your assessment for lesson 2 of this unit. All right, that's it. Thank you.